All right, so we've talked about circular motion, and I've been spending a lot of time in circular motion because it tends to be a sticky point for people. The linear stuff is a little bit more intuitive, which is a word in physics we used to mean like easy for your brain. So we're going to talk about non-uniform circular motion. Up until now, what kind of acceleration did we have? Which way did it point?
Up? Or towards the center?
Towards the center of it. For circular motion, yes. We've had lots of different kinds of acceleration. It's pointed up, down, to the side, and down a ramp. But in terms of circular motion, we've only dealt with acceleration in the radial direction. So remember, when things are moving in a circle, right, if they're going at a constant speed, the only acceleration, because remember, constant speed usually means no acceleration, but because we're turning, the only acceleration comes from turning. So that acceleration inherently has to be perpendicular to the speed or velocity in order to create a turn, okay? If you had an acceleration parallel to your velocity vector, what does that do? Yeah, it makes you speed up, and if it's anti-parallel, it will make you slow down, just like we talked about when we were talking about kinematics, okay? So accelerations parallel to your velocities speed you up. Accelerations anti-parallel or opposed to your velocity vectors are going to slow you down. So what that means is if you're turning in a circle, obviously if you're going from stopped to moving, are you accelerating? Yeah. You're going from one velocity to another. So anytime you go from stop to moving, that's a non-uniform acceleration. So you have more than just the acceleration pointing towards the center of the circle, okay? So in doing this, and we've already introduced these variables, you know, the angular velocity, the angular acceleration, we've already used them both on an exam and in the last class section, but they become very important now that we're dealing with acceleration, because remember, angular acceleration relates to tangential acceleration, which is the acceleration that causes the tangential velocity, the spinning speed, to speed up and down. Okay, so we're going to go back to those variables, and we've talked about them already. I think people are a little confused about them still, so that's why we're going kind of slow through this. But I want you to get used to them and remember that angular velocity, angular acceleration, and sort of angular position, which is just the angle, theta, those are both radius independent. So whatever spinning object it is, like if you're spinning this can, the speed everywhere on this part of the can would be the same for the angular speed, okay? The linear speed, the regular speed v, depends on radius from the center. So it depends on your distance from the center, but the angular quantities do not, okay? The other thing about angular quantities, if you want to go back to the linear quantities, you multiply them by r. That's what it means mathematically, that they don't depend on r. So you have to put r back in to get your linear quantities, meaning velocity and acceleration, the regular ones. And then last but not least, the way that these relate to the traditional linear velocity and acceleration is they relate to the tangential ones, okay? So you can only make, it's not, if you find angular acceleration and you multiply it by r, you get tangential acceleration, okay? You never get radial by using these quantities. So these are all the tangential quantities, essentially. Okay, let's try a problem. If you don't have a clicker, go for it. Oh, man. Oh, and I think this has an animation, just in case that helps you. There we go. So remotely, it's either A, B, or C. Please discuss. We'll vote again. It's not drastically different. And the chat's saying mostly C. Okay, so I guess we have to have a conversation about direction. When we talked, and we talked about this briefly, but a while ago. So when we talked about these quantities in terms of kinematics, right? Which way is positive when you're spinning? So remember that whole unit circle thing? You guys remember that thing? So when you look at the unit circle, does it go clockwise or counterclockwise?
Counterclockwise.
Counterclockwise, right? So this is 0, right? This is pi over 2. This is pi. This is 3 pi over 2. So essentially you're going counterclockwise, okay? Clocks are really the ones that are messed up. Like if they really wanted to obey math, then first of all, we'd probably put noon here, and then it would go this way, okay? So it's annoying. Why do clocks go clockwise? Is there like a specific reason?
You can't make them go in a square.
I just mean versus counterclockwise.
Oh.
But yes, they are round. Why do they go clockwise instead of counterclockwise? Because of the word clockwise. It turns out it's just you have to have it be standard, otherwise it gets really confusing. Because if someone has a counterclockwise clock and you look at it and just glance at it, it's really hard to read the time without getting screwed up. I actually have a counterclockwise clock in my office. It's not working right now because I have to climb on the desk to change the battery, and that seems dangerous. So, it still you can still tell time, but we standardize things like our, when we have particular variables we use for quantity, those were made up by a person. They're not like some universal law bestowed upon us by the physics gods. Like we just pick something and then we try to all use the same thing so we don't get confused, okay? But in math, unfortunately, clocks are wrong and we go counterclockwise, okay? Counterclockwise is the positive direction. So if you picked that these are opposite, you got the main concept right. So if you said that one of them's positive and one of them's negative, good, because it's slowing down, so you got that part right. But to be technically correct when we're starting to deal with rotation, in order for something to be positive, it has to be going counterclockwise. Okay, so in this case, because the fan is spinning clockwise, the speed, the angular velocity, omega, is going to be negative, and because it's slowing down, we know the acceleration has to be opposite to that, so that has to be positive, okay? So that's going to be an answer B. Oh, yes. All right, so for angular acceleration, remember, slowing down, these are the two ways you could slow down, right? You could either have if you have a positive angular velocity, right? That would be counterclockwise, and then you have a negative angular acceleration. If you have a negative angular velocity and a positive angular acceleration, and then obviously if they're both positive or both negative, you're going to be speeding up, okay? So just as a reminder, here's our sort of kinematics equations that you all love so much and you should be very familiar with now, okay? So there's head shaking. And then if we want to translate these over to rotation, they're the exact same equations. So if you know these, you already kind of know these. All you have to do to get from here to here is divide by r, okay? Because remember, v divided by r, omega, right? Alpha divided by r, or a divided by r, alpha. So these are the same equations. They work the same way. They just have slightly different variables, and we've taken out the radius here, or like the distance from the center of a spinning thing, all right? And just as a reminder, remember, delta S in this case is the linear distance. It represents a dummy variable, meaning it represents x, y, or z, or r, theta, phi, or any system that you're using of three-dimensional coordinates, okay? So we use S just to be general. It's the same as the change in theta times the radius. So the change in theta this is the arc length, right? Change in theta is the angle times the radius, right? Velocity is just angular velocity times r, and this is tangential velocity. Tangential acceleration is just angular acceleration times r, and r is just your distance from the center. Okay, so it's not necessarily the radius of the object, it's wherever you are on the object with relation to the pivot point or the center of rotation. Okay? All right. Remember, for dynamics in 2 dimensions, there's different ways to get acceleration, changes in speed, and changes in direction, okay? So up until now, we've really been dealing with just the change in direction in terms of our acceleration for uniform circular motion because the speed was by definition constant. Now we're adding back in the ability to change speed as well, okay? So here's a quick question just so we remember conceptually how these vectors work. Really great job of doing the slides today. Okay, Mostly A, some C. Please discuss. We'll vote again, even though some of you may have seen the spoilers. Surprisingly, we all think it's A. But what's going on here? How would you represent this force? What might you do to sort of make this clearer?
Break it up.
Yeah, break it up into components, right? And so one of those components would be parallel or anti-parallel to the velocity. Okay, what does that one do? It slows it down, right? So remember, force is in the same direction as the acceleration. We're assuming this is the net force. So the component of force that points along this direction should slow down your velocity. Then there's going to be another component that points down like this. What's that going to cause it to do? Turn downward, okay? So any acceleration components perpendicular to your velocity cause it to turn. Anything parallel to your velocity will cause it to speed up or slow down, okay? All right. So this brings us to sort of a discussion of non-uniform circular motion. So remember, we have acceleration. Our radial acceleration points towards the center of the circle. Our velocity is tangent to the circle. Now we're going to add back in a tangential acceleration, okay? So this acceleration should cause this arrow to get bigger. This acceleration should cause it to turn, okay? It gets a little bit more complicated because, remember, this depends on the speed. So as this arrow gets bigger, this acceleration also gets bigger, okay? So we also, just as a reminder, as long as the tangential acceleration is constant, you can write it as change in velocity, tangential, over change in time. We can also relate it back to the angular acceleration. So we have a lot of variables to keep track of here. So just remember if you're in circular coordinates or radial tangential coordinates, okay? And so once you have this angular acceleration, now you can do kinematics the same way we did before. But remember, we did this a little bit when we talked about kinematics. What does this distance represent? Like, how do you go back and forth between this and a total distance? Let's say you get an answer that's like 5 pi. How do you figure out how far 5 pi is? What do you have to know? So what does 5 pi mean in terms of circles? Yeah, 2.5 rotations around a circle. Okay, so if you want to go back to a distance in meters, what do you need to know about that circle? You need its radius so you can find its circumference, right? So once you have an angular distance, you want to translate it back to a linear distance, you have to think about it in terms of circles. If you have a multiple of 2 pi, that's multiples of 1 rotation or 1 revolution, okay? So that's something people get hung up on a lot. But it's actually not that difficult to go back and forth between those things. The other thing is angular speed. How do we get back and forth to angular speed from, say, frequency? That's period. So angular speed is just 2 pi times the frequency. So if you know how fast something's spinning in terms of its frequency, you can translate that really easily to the angular speed. So these problems are going to end up giving you a lot of things like, you know, this thing is spinning at this RPM, and that would be your initial angular velocity, but you have to multiply it by 2 pi to make it work in this equation, okay? Cool. So start thinking in circles. Just like we were talking about before, when we sum up our forces now, we have to sum up our forces in terms of our radial forces, and that's what we've been doing. We've already dealt with the sort of the z forces because we have to use those for friction, but now we also are going to have forces in the t direction. So anything that's causing you to speed up or slow down, that's going to be your tangential force, okay? And these are a little bit subtle. So for instance, let's say you have what's something that spins that you use? Your toothbrush? Oh, yeah. Tires on your car, right? What causes those things to spin? The engine, right? So your tangential force is going to come from sort of a torque from your engine or the motor on your toothbrush, or if you have a drill, like the motor on the drill. So it's not as straightforward as some of the forces that where you're like, this thing is pushing on that thing, right? It is to some extent, but sometimes it's sort of built into the machinery. So if you took it apart, you would see the motor actually has something that it's turning, and that force is usually expressed as a torque. We haven't gotten to torque yet, but that can be translated to a tangential force, okay? All right, so we're going to try an example problem with a motor, because pretty much all spinning things end up having motors. So let me set this up. But now we're talking about a motor spinning on a 2 kilogram steel block. A motor spins a 2 kilogram steel block around a 0.8 meter long arm at 200 RPM. Once the motor stops, how long does the block take to come to rest? And we know the coefficient of kinetic friction between the block and the table is 0.6. Okay. So I'm going to draw a circle. We're going to do the top view and the side view like we did before. We're going to set this up just like a uniform circular motion problem. But the difference will be that this time we have a tangential component that we have to keep track of. Okay, so this would be our top view. So this is the center of our circle. Here's our block. This is our radius, which is 0.8 meters. So that goes here. We have a frequency of, so our frequency is going to be 200 rotations per minute. We have a mass of 2 kilograms. And what do we, and a coefficient of friction of 0.6. What are we looking for here? What's the question asking us for? A time, right? So we want to know what delta t is. We want to go from omega initial is equal to 2 pi times frequency, and then omega final is going to be 0 because we're at rest. Okay, so we'll start by drawing the picture, and then we'll write out the forces, and then we'll put together our equations, okay? So this is going to be both a force equation and a kinematics equation, right? Because we're asking for time. So what do you think we need to get from the force equation? Acceleration, right? That's how we connect force to kinematics. So, there's also a block on the floor. So from the side view, actually, I'm just going to oh, wow. Okay. Never mind. Okay. So what are the forces acting on this thing? Weight. Anything else? Yeah, there should be some tension. What else we got? The tension's here too.
Normal?
Yeah, normal force because it's sitting on the ground. And then let's say it's going in the positive direction. So let's say it's traveling this way, right? Oops. Oh boy. I lost the normal force. Oh. Wow. Having a good day on this. So let's say it's traveling this way. That's our initial velocity, right? Or if you want to, since we're using these circular, we'll say omega. And I'll make it a little curvier. So that's omega. All right. Which way is our acceleration going to be? Specifically our angular acceleration. Yeah, it's got to be the opposite direction of this because we know this is slowing down and then eventually stopping, okay? And then that means that which way do you think our force is going to be? And what kind of force would it be?
Negative friction.
Yeah, it's going to be a negative friction. So this is kinetic friction, which we know is mu k n, pointing in the opposite direction from the motion, right? So our initial speed comes from the motor. We're not actually dealing with a force from the motor. That's just giving us our starting speed, and then we're turning off the motor and it's going down to 0, okay? So here's all of our forces. What directions are these things pointing? So this should be Z, right? And then this direction we'll call radial. And then we can call our tangential direction this way or this way, right?
Wouldn't do it that way because of acceleration.
Yeah, okay, yes, that's the best strategy. But you can point it either way you want, just because then you just have to be careful with the signs. So yeah, tangential points this way. So this would be like over here, tangential, radial, okay? So when we sum up all of our forces, we're going to do our Newton's second law thing first. So to start out with, here's all our information that we have plus the forces. And then we want to start with Newton's second law. And what's Newton's second law?
Mass times acceleration.
Yeah, it's force equals mass times acceleration, and specifically net force. So we want to sum up all of our forces. How many dimensions do we have? How many force equations are we going to have? 3, because we have radial, tangential, and we have Z, okay? So we'll start with Z because that one's the most straightforward because there's no acceleration in the Z direction. So in the Z direction, we have normal force minus weight is equal to 0, which is the mass times acceleration in the Z direction. But remember, there's no actual acceleration in the Z direction, okay? Then we'll do tangential, or let's start with radial because we're more familiar with that. Okay, what's the force in the radial direction? Tension, which should be positive, and that should be equal to mass times acceleration. But remember, the radial acceleration is either v squared over r, or you could write it as omega squared r. Okay. All right. Last but not least, we have our force in the tangential direction. And that's going to be the kinetic friction, which I'm going to just straight write as mu kn just for simplicity, since I think we're familiar with that now. So instead of writing just friction, I'm just going to write it as its formula so we don't have to have so many equations. And this should be equal to mass times acceleration, okay? But remember, acceleration is equal to r times alpha. So I'm going to write that as mass times r alpha. Okay? And why would we do that? There's 2 ways we can go about this. We can solve for regular acceleration and convert it to alpha at the end, or we can just write this way so we get angular acceleration. But we know later we're going to need to do a kinematics problem. So in order to do the kinematics problem, all of our variables need to be circular or linear. So we either need, since we're given our speeds in RPM, it's probably going to be easier to start with angular speed, and that means we probably also want angular acceleration, okay, just for consistency. The other option is, if you just hate the angular equations, you don't want to try to remember them, you can convert everything to tangential and just plug it into the formulas that you're used to. But both of them will give you the same answer. The only thing you don't want to do is use linear and radial variables together, because you'll have some serious unit mismatches at the end, okay? So we have our 3 equations. What we're trying to solve for is angular acceleration. It looks like we probably won't need the radial equation in this case, because what we really need to solve for is alpha. Okay, so that's the main thing we're looking for the solution for. We know radius, we know the coefficient of friction, we know mass, and then we also know we can plug in the normal force. So we're going to do that. So remember, if you take this, you know N is equal to mg. So we can write mu k mg is equal to mr alpha. Nicely, the masses are going to cancel, and we'll get alpha is equal to mu kg over r. Okay? Okay. And remember, this thing we wrote here, this is just mass times acceleration, because r times the angular acceleration is just our linear acceleration. So we're still doing Newton's second law. Just a reminder that we skipped a little bit of a step there. So if we plug in numbers, we get 0.6 times 9.8 meters per second squared divided by r, which is 0.8 meters. So that's going to give us an angular acceleration of negative 7.4, 7.4 radians per second squared. Okay, that's our angular acceleration. Now, is that pointed in the clockwise or counterclockwise direction? Clockwise. So it could be, you can consider it to be negative, but really what matters is how we relate the sign to our speed. Okay, so if we choose our speeds to be positive, then this is going to be negative. So whether you get that from the math or whether you get that from looking at the picture and understanding how the formulas work, that all of those should give you the same thing. Okay, so this is our angular acceleration. That's our first step to solving the next part of the problem. Okay, so I'm going to move this over a little. So we have some space for the next part of the problem. Okay, so now that we have the acceleration, what are we looking for? Time, right? We want to figure out time. So we have initial speed, we have final speed, and we have acceleration. So we probably want to use the equation that has initial speed, final speed, acceleration, and time. That one is going to look like this. So that is omega final is equal to omega initial plus a alpha. Ugh. See, it is hard to keep track of. Alpha delta t, okay? We know what omega final is, but we still haven't really calculated omega initial. How do we calculate omega initial? 2 pi frequency. And we have to do a unit conversion, okay? Because we're given our frequency in rotations per minute, but remember everything needs to be in seconds. So we get 2 pi times 200 RPM. So that's, and how many seconds are in a minute? Yeah, 1 minute divided by 60 seconds. And so that should give us, sorry, I ran out of space, but that should give us an angular frequency of 21 radians per second. So that's our initial angular speed. And then here is our final angular speed. So we're solving this for delta t, which means that we get, so this is 0. We get alpha minus omega. So omega naught divided by alpha. Okay. You'll notice there was a negative sign that should be introduced there because this part is 0. But remember, this is negative compared to the speed, so that gets rid of our negative sign. What I mean is, like, when you subtract this over, it should give you negative omega naught, okay? But you know that the angular acceleration is also negative, so that shouldn't be a problem because we don't want to end up with negative time, okay? We plug in our values and we get 21 radians per second divided by 7.4 radians per second squared. Anyone want to give me an estimate of what that answer is going to look like? Little under 3, right? Because it's about 21 divided by 7, but it's a little bit bigger than 7. So that's going to give us 2.8 seconds. So it takes 2.8 seconds for this thing to come to a stop. Okay, so I know this looks slightly unfamiliar, but the steps are similar to what we've been doing, okay? We're setting up the problems, we're looking at our knowns and unknowns and what we're trying to solve for. Then we draw a picture, figure out all the forces, we sum up all our forces. Because we know the quantity we wanted was kinematics related, we solve for acceleration and then find the relevant kinematics equation, okay? Yes?
How come at the end, the 7.4 is negative?
Because I did some wizardry over here. So if you really want to go through that more slowly, what ends up happening is, sorry, I accidentally moved that. What ends up happening is you have omega naught is equal to negative alpha delta t, right? And then you get delta t is equal to negative omega naught over alpha, and then you plug in the negative alpha, and it should give you a positive time. Okay? But the key here is when you're solving this equation, you know that this has the opposite sign from this by definition. Yeah, because they're going in different directions. And you drew that here, but it's representing it in the math. The tricky thing is you want to know that just by looking at it. Like if you're trying to keep track of all the negative signs and you don't understand conceptually what's going on, it's really easy to just add when you should subtract or add the negative twice. So it's really key to know these things are going in opposite directions. Right when I look at this equation here, I should know that, okay, if I end up in this situation, omega is going to have to be opposite from alpha, sign-wise. We're going to do another problem, but there's an introductory video to watch about a hamster.
Before he goes, lying to the teacher who knows he knows. He's better than he should have, but he's lying to yesterday. And he finds the sound as the day begins. The letterbox is open, your cash falls in. I'll meet you at the office just before we start clocking.
So thanks to this delightful YouTube video, we can do a problem based on this hamster's experience, in case you were wondering how physics could relate to your everyday life. All right, we're back. It's a long question, so there's a lot of reading. But basically, the video, so what was that hamster wheel hooked up to? Let me know what that thing above it was. So anybody ride a road bike? No. Okay. Has anyone ridden a bike before?
I do.
Several people have ridden a bike. Okay. If you want, so the road bikes have these little computers, and basically it has a little monitor and let me turn that off. A little monitor and then a thing you attach to the wheel and then attach to the frame of the bike. So it measures how many times that thing goes past the sensor, right? So every time the wheel turns, it marks one rotation, okay? So that's how a bike computer measures the rotation. So someone just attached that to a hamster wheel, which is still a wheel, and so that's how it was measuring the speed and the rotations, okay? And when you have a bike computer, all you have to do is calibrate it to the circumference of your wheel. There's usually a place where you can put that in. If you buy wheels, I think it does it by diameter, but the math is all the same math, right? If you know the diameter of your bike wheel, you know the circumference, and then it just if you want to know how far you've ridden and it's given you that many rotations, you just multiply that by the circumference of the circle, okay? So this hamster wheel is attached to a bike computer. So that's why we know it's going 6.8 kilometers per hour. If you watch the video again, it says 6.8 kilometers per hour. These are all values I got from this delightful YouTube video with a very high production value. I decided that he spun around 12.5 times before he fell out, just because he starts at the bottom and he ends up at the top. So that's an extra half rotation. So I don't think these people were planning on this becoming a physics video, so they were not super precise. And then we're going to estimate that hamsters weigh about 150 grams based on having held a hamster once in my hand. So the wheel has a radius of 5 centimeters. The first thing we want to figure out, which I will do with you, we've talked about this in the previous class, but we didn't actually do the calculation. We want to know the critical speed the wheel has to have for the hamster tick to create a complete circle without falling out of the hamster wheel, okay? And then the next thing we want to know is what was tick's average and tangential and angular acceleration on the, so both accelerations, both the angular and tangential accelerations. And we're asking for average because we're going to have to assume them to be constant in order to use the equations that we're given without doing extra calculus. Okay, so let's start out by calculating what happens when does a hamster fall out of a wheel. So we have to draw a force diagram for this. So I'm going to draw this hamster. Oops. This is my hamster. I'm sorry. It's not very good. Okay, hamster, upside down. What are the forces acting on your hamster at this point? There's a normal force and weight. Which weight points down? Which way does normal force point? Also points down. All right. What did we say? And so there's, it's spinning. So there's also an acceleration in the radial direction. Okay. What did we say has to happen to normal force for us to be in contact with something? Or to not be in contact with something? So if you're not touching something, do you have a normal force? No. So at the very point, at the minimum speed you need, right, you can call normal force 0. And we're doing that because that gives us the minimum amount of speed we need. If normal force is greater than 0, it's pointing down, right? The hamster's in good contact with the wheel. If normal force is 0, it's right after the hamster has lost contact with the wheel. Okay? So we're using that. So that means if we sum up our forces in the radial direction, right, we have weight mg plus normal force is equal to m, and we're looking for speed, tangential speed squared over r, okay? But what we're going to do, the condition to find the minimum speed is that, I can erase it, but that wasn't what I meant to do, that normal force goes to 0, okay? So it's the minimum possible normal force, so right before the hamster falls off would be what we're actually looking for, but the critical point is that normal force is equal to 0, okay? All right, so then we just solve for speed so that we get mg is equal to m v squared over r. We can cancel out the m's, so v is going to be the square root of g times r. Okay, this is generally true. We'll call this v critical. So this is this is the minimum speed you need for something to not drop out of a loop, an upside down loop. Okay, if it's moving in a circle. So we can plug in our values. That's going to be 9.8 meters per second squared times 0.05 meters. So our minimum speed should be 0.7 meters per second. So that's we'll call that V critical. And or V critter in this case. And we'll just save that for later. Okay, that's our first part of the problem. All right. And then we also want to know what is his average tangential and angular acceleration. So in order to do that, we have to do what kind of problem?
The acceleration?
Mm-hmm.
Kinematic.
Yeah, we're going to do kinematics. Why do we want to do kinematics? What are we given? We have this speed, right? So what's this speed? Is it initial or final? Initial, right? So we have an initial speed of 6.8 kilometers per hour. What do you think we have to do with this? Convert it to what?
Meters per second.
Meters per second. So remember we have 1 hour, 3,600 seconds, and then 1 kilometer is 1,000 meters. So that's going to give us 1.89 meters per second. So that's our initial speed. What's our final speed?
be the critical speed.
It's the critical speed, right? Because it starts, we know the speed the hamster starts at, right? Then because before that, he's running. So the start of this problem is when he stops running, he gets stuck and starts spinning around on the wheel, okay? At that point, he's no longer propelling the wheel and the speed starts to slow down because he's not doing his little friction foot thing, okay? So as soon as he stops running on the wheel and gets stuck to it and starts going around in circles, that's our initial speed. That's at 6.8 kilometers per hour or 1.89 meters per second. And then the end of our problem is when he falls out of the wheel, and we know what speed that happens at, okay? So our final speed is the same as v critical, which is 0.7 meters per second, okay? So we also know that he spins around 12 and a half times. What does that tell us in terms of kinematics?
Revolutions per minute, like the angle.
Well, speed is the same as revolutions per minute. So if he goes around a circle 12 and a half times, is that a speed? Is that an acceleration? Is that a distance? Is that a time?
The distance.
A distance, right? And how do we make that a distance?
Finding circumference.
Yes. Yes, we find the circumference. So how do we get our distance? And are we using linear or radial variables here?
Or, well, for the distance.
So far we have v's, right? Not omegas. So we're probably just going to use the regular formula. We can convert these to omegas by dividing through by the radius, but why? We already did them, okay? So we're probably going to use a standard equation. So we need our distance in meters. So we need basically S, which is the, I don't know, arc length, I guess. It's like a really long arc length. So in order to get, we call it X, if that makes people feel better. I don't know. You want S or X?
X.
All right, let's call it X. So delta X is going to be equal to 12.5 times the circumference. So 2 pi times the radius. So we'll do 12.5 times 2 pi times the radius, which is 0.05 meters. And that's going to give us 3.93 meters. Okay? Cool. So we have X, we have two speeds. What kinematics equation do you think we want to use? What do we not have?
Acceleration.
We don't have acceleration, but we have to find that. What else do we not have? Time. So since we don't have time, we want to use the only one that doesn't have time, and that's v final squared is equal to v initial squared plus 2a delta x. Okay? So we're going to solve this for acceleration. So we just do some algebra. That's v final squared minus v initial squared is equal to 2a delta x. And so a is going to be equal to v final squared minus v initial squared divided by 2 delta x. So we just plug in our values. That's going to be 0.7 meters per second quantity squared minus 1.89 meters per second squared divided by 2 times 3.93 meters. So plugging all that in, we're going to get an acceleration of negative 0, very small acceleration, 0.392 meters per second squared. So that's our acceleration. Okay. And that's this part of the problem. Average, tangential, and angular acceleration. That's our tangential acceleration. You want to put a little t there if you want. Does it make sense that it's so small? Do hamsters get a lot of acceleration? Not really. So yeah, it makes sense that it's going to be pretty small. What about that angular acceleration? How do we get that? Yeah, you divide by r, right? So remember, A tangential is equal to alpha r. So if we want alpha, we just take A tangential divided by r. So we say negative 0.392 meters per second squared divided by 0.05 meters, and that's going to give us negative 7.85 radians per second squared, and that's our alpha. And why are these negative? I mean, they're negative because we're just assuming the speed is positive, right? And since it's slowing down, it has to be the opposite sign. Very lively today. All right, any questions about this? So circular kinematics, not terribly different from linear kinematics, just finding your quantities from the problem that's a little trickier. So if you're given frequency, you should think speed. If you're given rotations, you should think distance. And then angular acceleration is just slightly different from the way we describe acceleration. Okay. The only real curveball here is finding the critical speed and knowing that the end speed isn't 0. Okay. Cool. One more video. So remember we talked about the rotating carnival ride where the bottom drops out? Here's a video of that. It doesn't have any sound, so you're not missing anything. These people are definitely going to throw up later. But anyway, what is the what is the force holding them in place? That's not force, right? What's the centripetal force in this case? I think somebody said it. The normal force, right? So, but what do you feel when you're in this ride? What does it feel like it's happening to you? You're getting pushed into the wall, right? And remember, we talked a little bit about this, but this is a fictitious force, okay? Whenever we accelerate, our bodies perceive a force in the basically equal and opposite direction from the force we should draw in the force diagram. Just like when you're sitting in the driver's seat and you step on the gas, right? It feels like you're being pushed back. But that's just the equal and opposite force to the chair pushing forward on you, okay? So the acceleration we know is forward, the car is moving forward, you're moving forward, but you feel like you're being pushed back. That is a fictitious force. So this is a time when you don't trust your feelings and you draw what should go on the force diagram, all right? So the centripetal force is a real force that pushes an object towards the center of the circle. We did a whole lab on it. It's always pointing towards the center of the circle. The object, in this case, like if you're in one of these guys, you, is going to feel something called the centrifugal force, which is the force that makes you feel like you're being pushed into the wall behind you. Okay, the centrifugal force is equal in magnitude and opposite in direction, but they are not necessarily an action-reaction pair, and you wouldn't draw that force anywhere. It's more of a perceived force because of the way our brain and senses process what's happening to us, okay? So we don't necessarily think exactly in physics. We just think in like survival. So we feel something pressing against us. We think we're being pushed backwards. Okay, just for some clarity, and yeah, that is all we got for this chapter.